Log on, tune in, find out. Another good idea from Cambridge.
Last talk of this afternoon session. Very pleased to have Robert Rowley here from USC from Los Angeles. He'll talk to us about permutation groups and covariance of curves.
Thank you, Gerhard, and thanks to the organizers for inviting me, and it's a pleasure and an honor to be here. John has had a huge influence on my career. I mean, mostly because without him, there would not be a classification. I think it's pretty clear from what Michael said in his talk that there was he created a revolution in group theory with his thesis, with the Veit-Thompson auto-order paper, and most especially with the N groups. He's also made, of course, lots of other contributions in representation theory, sporadic groups, inverse Galois problem, and projective planes. And also, he's showed me he and Diane lots of hospitality every time I visited Cambridge. In fact, the first time I came to Cambridge in 1990, Jan invited me and wasn't here when I arrived. But he did arrange for me to have dinner with the Thompsons and with his wife, Ruth. And I've stayed with John when I visited here, and they've always been extremely hospitable to me over the years. As Dan Siegel said in his talk, that you can use the classification to prove lots of things that are not so obviously related to finite simple groups. And he said, well, there's this list. And in fact, of course, there is a list, but the important thing is not that there's a list. The important thing is that we know what they are, that they have structure. They're the fixed points of Frobenius morphisms of algebraic groups. And so we can use their structure, their geometric structure that one can use. And also, of course, the other Abel Prize winner besides John, Tietz, told us about what BN pairs look like and buildings and so forth. And so we have lots of machinery that we can use about it. If you just have a list and you had to check every single group separately, I mean, for example, when you use the classification, very often checking the 26 sporadic groups can take longer than doing everything else. So it's important to have this machinery around. And of course, the other person in the audience that Michael has had a big influence on my career, when I was a postdoc at Caltech, and of course, as Danny Gorenstein had said, the classification would have taken much, much longer without Michael. And that was before they did quasi-thin with Steve. So. And in fact, speaking of algebraic groups, the third person I think who had the most influence on my career was Bob Steinberg, which is where I learned about algebraic groups as a graduate student at UCLA. So what I want to talk about is actually things that came out of some joint work that John and I did quite a while ago and is still ongoing, relating problems about maps between curves and using permutation group theory to say things about those, which are perhaps surprising, although perhaps not as well. So let me just, the general setup, I'll have K will be a field, and I'm going to assume it's always perfect. I won't say that anymore, and for most of what I say, it won't make any difference anyway, but just in case somebody catches me. And in fact, most of the time, K is going to be either finite or algebraically closed. And I have X and Y smooth projective curves. Defined over K. And I'll have some morphism. So a non-constant morphism of degree n. Bigger than 1. Also defined over K. So for a lot of what I'm going to say, think of a polynomial or a rational function, x and y are P1. That's a quite complicated case already for a lot of the stuff I'm going to do. Okay, so I want to get groups into the picture here. So the setup is as follows. We think of it, and I also want to assume that f is geometric, and I'll say what that means in a minute. So the setup is we translate this to extensions of fields. We have the function field of x. And let me also, all my morphisms will be separable. So we have some extension, separable field extension of degree n. We can take the Galois closure, and this will be some curve, perhaps over an extension field. And so this is the picture that I want to look at. So this is the Galois closure of this over this. So I will let A be the Galois group of L over K of Y. Sometimes this is called the arithmetic Galois group or the geometric, or the arithmetic monodromy group of this setup. G will be the Galois group of L over K prime of Y. And observe that A mod G is isomorphic to the Galois group of K prime over K. So what I meant by geometric is that there are no extra constants in this function field. So K is algebraically closed in here. And that assumption means that this degree is also n. So again, if you think of a polynomial map or rational function, you always have that. And then this quotient is just the Galois group of this. I will let H be the Galois group of this extension. And so we have the usual action of the cosets at A and H. And A is transitive, but in fact, G is also transitive. Because, again, by the assumption here, G is actually, if I take this Galois closure, I get G, and so it's transitive on the roots there. OK, so this is the setup. So we have some groups there. And the point is I want to look at various questions about maps between curves and say something about what you can say using some non-trivial results about permutation groups. So let me state a curious theorem. So let's let f of x be a polynomial of degree n. Characteristic of k is p, which may be 0. And suppose f is indecomposable. So it can't write it as a composition of non-trivial polynomials other than where one of them is degree 1. It turns out it's equivalent to saying you can't do it as rational functions. So in this picture, if I think of a polynomial, it's a map from P1 to P1. So what I have is k of x over k of f of x is in the function field case there. And to say it's indecomposable is saying that that's a minimal field extension. So there are no fields in between. But f decomposes over some extension. And in fact, k prime will always work. If it does, it will be the k prime that's in that picture. Then one of the following holds. I learned that abbreviation from Richard Lyons. So n is a power of the characteristic. OK, and these actually do occur. So maybe just the nice thing, I like these kinds of problems quite a lot. I mean, there are three nice parts to them very often. First is translating the arithmetic or geometric question into group theory. Secondly is solving the group theory problem. And thirdly is saying which group theoretic solutions actually correspond to the geometric or arithmetic problem. Okay, so in this case, there's lots of examples. It's theoretic. It may be possible to someday classify these things, although it's because it's a polynomial, not really because it's a mess. Where do these come from? Well, let's think of what this says in terms of the group theory. And it turns out it actually doesn't matter that it's a polynomial. What matters is that there's a totally ramified point. So when you have a polynomial, there's exactly one point over infinity. And that's what I mean by the point is totally ramified. And this is a theorem of myself with Jan quite a while ago. And then, in fact, more recently, in joint work with Zeev, we've actually classified all the polynomials. So Jan and I sort of did the group theory and then showed that there were examples that corresponded to this. And then Mike Zeev and I actually classified all such polynomials. Well, what's the group theory? What's going on in terms of the group theory in this case? So what this is telling you is that A is primitive on A mod H. So in this, and G is not primitive. So the point is, as I said, you can really reduce to the case where you can show that it just depends on K prime. So it's saying that K prime X over K prime Y is not a minimal field extension. So there's something in between there. So it's saying that the point stabilizer of G is not maximum. And what does the totally ramified point have to do with anything? Well, it tells you that A is equal to H times I, where I is the inertia group. Of the totally ramified point. In particular, some point. Now, the thing about inertia groups, well, first of all, factorizations are fairly rare. Although people working in curves didn't understand that, I think. But if you're a group theorist, you realize that this is not, you don't always have this, and especially inertia groups are not random subgroups. They're cyclic mod P. And particularly for your characteristic 0, they're cyclic. So I should say this theorem depends on the classification of finite simple groups, but not in characteristic 0. Characteristic 0, there's actually a nice little exercise. The point is, this assumption tells you have an n cycle. And sort of that tells you that in G, which you want to try to prove G is primitive, that the sublattice of subgroups between G and the point stabilizer is actually isomorphic to a part of the sublattice in the cyclic group of order n. In particular, there's a unique thing of each order. So if there was something in between, its normalizer would also sit in between up and stairs in A. So it's actually, that's pretty easy. I don't know who proved it in first characteristic 0. Actually, one of Jan's colleagues, Alan Bearden has worked on that. And I mean, more subtle questions. OK. And then one wants to classify primitive groups, which have a factorization like this, in which it has a normal subgroup, which is not primitive. And you see that you get down to these two situations. And what happens here is this is the, it's easier to say what G is. Well, it doesn't matter. G is, in this case, PSL27. And here it's PSL211. And that's G, and A is PGL. And you can see that there's a subgroup which is not maximal down in here, but its normalizer is maximal in the bigger group. OK. So I'm be hard pressed for somebody just thinking about polynomials to prove this theorem. OK. All right. All right, here's another theorem which, the other nice thing about thinking of these problems is that you actually think about some group theoretic concepts that you probably wouldn't have thought about without this context. And I'll mention a couple of examples in that context. So here's another one. If K happens to be finite in this setup, then the K prime over K can't be that big. So the extension of constants you get is at most n. And what's the group theoretic statement of that? This is essentially equivalent to the following group theoretic fact, is that suppose that A is a transitive subgroup of Sn, G is normal in A, and A mod G is cyclic. Then this implies, and if G is transitive, you have strict inequality. Now this seems like a very easy statement. You should give it to your undergraduate group theory class. You have a transitive subgroup, a normal subgroup in it with a cyclic quotient. It can't be very big. And I'm not convinced there isn't a proof that doesn't use the classification, but at the moment the only proof does require the classification. So if somebody comes up with one before the end of the hour, let me know. Okay. And again, I mean, the reason I thought about this was precisely because of the context it came up in. In some sense, it's a very natural group theoretic question that nobody had looked at it before. But so, all right. So another invariant that I want to look at is the genus of X. So I'll write this as the genus of X. And the point is that some invariant attached to your curve, as I said, P1 has genus 0. And that's already an interesting case. Here I'll give a definition of the genus, which is, perhaps fairly elementary. So maybe, I don't know. So if you take the Jacobian of X, so these are just formal sums of points, finite formal sums of points, modulo the divisors of functions on X. And it turns out if you take the n torsion in this has size n to the 2g as long as n, the characteristic doesn't divide n. So this defines the genus. And also, it's useful to, so if X happens to be, if you have a Galois extension, if F is a Galois map, then this n torsion is also a module for the Galois group. So if G acts on X, then we take the n torsion in the Jacobian. Let's take n to be a prime now. So let's say R is prime. So this is a module. And it turns out, again, as long as R is not the characteristic, the module is essentially the same. Well, OK, let's suppose that R doesn't divide the order of the group. So you can think of it as a module in characteristic 0. Look at its trace. It's independent of the prime. And even for the primes that do divide the order of the group, if you take the inverse limit of the powers of R, you get a module over ZR, R at X, and that's still, and then take it over the field, it's still the same module. And I don't know, was Tate prove that, or was that even earlier? Okay. Right. Well, Tate has been around a long time. Anyway, so we can use, and I'll mention how this can be used later on, in fact. OK. So this is called the Tate module. So as I said, it's independent. If R is P, then it actually has smaller size, and there's things one can do, but It's trickier. Okay. And there's also the Riemann-Hurwitz formula, which relates in that setup over there what's going on. And it says that 2 times the genus of x minus 1 is equal to minus, 2 times the degree, the genus of y minus 1 plus okay, I'll call them x's, where for some, well, let me just put it this way, for some xi in the group G, and where the index of xi is n minus the number of orbits of xi in the permutation representation. But there's other conditions on xi. In the special case where g of y is 0,
So here they're asking all the parameters characteristics serious. This will not be true.
no, this is right, and this is characteristic 0 or tame. Characteristic 0 or it's tame, if all ramification is tame. And if the genus is 0, then in fact what you have is that G is actually generated by the xi's, and the product of the xi's is 1. In positive characteristic, there's an analogous formula, but it's more complicated. So in general, there's a similar formula. Involving the inertia groups here, but it involves the higher ramification groups as well, so it's much more complicated. But in fact, a nice way of thinking of this is, in fact, it's really not the character formula. This is really you really view it in terms of the Tate module as a representation, and you're evaluating it. You get the character for the Tate module, and you evaluate it the identity, and this is what you come out. But you can in fact identify it at other calculated other elements, and it actually tells you something about sort of the genus of various subcurves inside there. All right. So a nice observation from the fact that let's take this to be 0, and let's suppose, so Ree made the following observation, that if G is generated by x1 through xr, product xi equals 1, is transitive in Sn, then this implies that the sum of the index of xi is bigger than or equal to 2n minus 2. And what was his proof? This number essentially is the genus of something, so it's bigger than or equal to 0, or this difference. That was his first proof. Feitlin and Scott gave a second proof, a very easy elementary group theory proof using permutations. But then Scott gave a linear algebra proof. So he proved a version of this where instead of being transitive in Sn, you think of it inside GL. And he got a very nice formula, which turns out to be immensely useful in group theory. And it's had lots of consequences. A way of proving you can't find generators for a group in certain cases. And it's in fact been immensely useful. And it's an elementary proof. His proof is basically the rank plus nullity theorem. But it's had, it's really been an important theorem in finite group theory, and it wouldn't have been, I don't think it would have been discovered without sort of this point of view. Okay, so let me tell you what John and I started thinking about back in late 80s, around 90, I guess. We published a paper on it. And it says, suppose I fix G, and so now I'm going to work over the complex numbers in this case. So in particular characteristic 0, or if you want, just tame. Just assume you have tame situation. All branch points, all inertia groups have order prime to p. And you look at this setup, what are the possible composition factors of this Galois group G? And John said he asked a couple of people, in particular he asked Barry Mazur, if you fix G, will that have any influence on the group? And I think Barry said, well, not that I can see. But that's because he doesn't do permutation group theory. If you're a permutation group theorist, you would realize that there really is some constraints on this. And so the answer, the theorem,
So G is the genus of what?
G is the genus of X. Right. And the only interesting case is when Y has genus 0, really. Because if you look at the Riemann-Hurwitz formula, if Y has genus 2 or bigger already, you see that the sum of the index doesn't matter. You're already going up basically linearly with the degree. Genus 1, it's not much harder to prove this similar kind of thing. So it's really when Y is a P1 that there's only anything much interesting to say. And the theorem is the composition factors, so the possible composition factors are cyclic, alternating, and a finite list depending on G. I mean, it's fairly easy to see by Riemann's existence theorem that any group occurs for some genus. But for a fixed genus, you only get finitely many more. It's also easy to see that the cyclic group occurs, kx over kxp. And if you take a generic thing of degree n, then you'll get the symmetric group. So those, or from the Riemann-Hurwitz formula, you can just write it down using involutions, for example. Now, what this exact finite list is,
If you fix the genus, the order of G is bounded.
no.
It's the genus of the top.
No, that's not. It's not Galois. It's not Galois. It's not Galois. So the genus of Z can be arbitrarily large. Yes. It's not Galois. That's the whole point of this, right? However, but the idea behind the proof. So I should say this started. Was called the Gorel-McThompson conjecture, and John and I worked on it. I had my first student, Michael Neubauer, worked on it. Michael Aschbacher contributed to this, Liebeck and Saxel, Liebeck and Shalev, and the final step was Kai Magard and Dan Frohart did this. So there were probably a couple of dozen papers involving this. And it's still not done because in some sense the first part of the proof was reduced to the case where it's indecomposable. And so now you have a primitive permutation group. And one would actually like to, I think it's doable, let's say for a small genus like 0, 1, or 2, you should actually be able to get the complete list, assuming it's indecomposable. And Kai Magard and Dan Frohart and I are working on that, and eventually, I hope, before I retire, we'll finish. But I'm not convinced. I'm not absolutely sure about this. But it's it turns out it's actually a reasonably short list. Okay. And what's the idea? What's going on in terms of the permutation group theory that's here? So the idea behind this is that suppose that G is a primitive permutation group. And suppose G is in G is not the identity, and G fixes more than half the points. Well, then this implies that G is essentially, I'll say what I mean by essentially in a minute, the alternating group or symmetric group. Or G is sp2n of 2, omega plus or minus 2n of 2. Actually, alternating groups are acting on K sets. And here, it's very specific actions. And moreover, in this case, G is a transvection. And it's still true that G fixes almost half the points, moves almost half the points. So what I mean by essentially is, well, you could have a Reith product, or something close to a Reith product, and then in one of the composition factors. So it could be a direct product of alternating groups or direct product of one of these guys. But, and now the point is, as Sarah pointed out, in the case where it's Galois, from the Riemann-Hurwitz formula, you get a bound, and so you're done. Well, what this theorem essentially tells you is that you're not so far off from the Galois case most of the time, except in this situation. But of course,
What's the scale? Particular case, what's the scale? The scale was a count field.
Sorry, M sets of size M, on subsets of size M.
For some M.
For some M. Yes, for some M.
But you don't tell.
Well, in terms of the theorem, it doesn't matter because it's the symmetric. We're allowing the alternating group is one of the conclusions. But in fact, later on, we will care. And in fact, there is a result, which I'll mention in a minute. Okay. Now, it turns out, well, so this is a theorem of Kai McGard and myself, and based on some earlier work that Jan and Martin Liebeck had done. And of course, this is classical. This goes back to the beginning of the roots of permutation group theory. Manning had results of this. You want to classify primitive groups which contain elements that fix lots of points. And I guess Babai has the best bound, which doesn't use the classification. This does depend on the classification. Okay. So here's another problem that's related to this. Suppose that I have this set up again, degree n, and again, characteristic 0. Well, I'll say something in characteristic p as well. And suppose that x sub g is generic. Okay, so I'm sure this is a little vague. What do I mean by that? So what do I mean is the following. Especially in characteristic 0, what it's telling us is that we have this group, we have this data up here. So in particular, we've got this permutation representation. We have branch points. So what we have are these, the collection of inertia groups. And I'm saying fix that data, the degree, the permutation representation, the inertia groups, and look at all curves of genus G which admit such a map with that data. And to say that the map isn't generic means that you can realize a dense subset or an open subvariety of the moduli space of genus G curves with that data. So that's what I mean by generic. If this is genus 1, for example, all it really means is that you can do this with a curve whose J invariant is transcendental. Okay. So Zariski proved in the 30s that if G is bigger than 6, G cannot be solvable. And the way his proof was group theoretic. It was completely group theoretic. He just translated it to group theory and used some fairly easy group theory of solvable primitive permutation groups and the Riemann-Hurwitz formula.
How could you use generic?
Okay, so what is generic? So let me tell you what generic. So what does generic imply? Well, first of all, is that it tells you two things. Suppose that I could factor this through. That if I had this, then it implies that the genus of y prime is 0, which of course implies the genus of y is 0. Let me assume G is bigger than 1. So that's the first thing he observed, is that so the point is the generic curve doesn't map onto any positive genus curve. So that's one thing. And why is that? Because the Jacobian, for a dense set of the moduli space of genus G curves, the Jacobian is absolutely simple. And here, it's not absolutely simple. Okay. I don't know if that was his proof, but anyway, he made that observation. And the second observation is that it implies that the number of branch points is at least 3G. So the number of points that are ramified. And why is that? Because the moduli space of curves, the dimension of this is 3g minus 3. And so the point is, if you look at this you can make a moduli space out of the set of covers with this data. It's a Hurwitz space. And it has a mapping onto the branch points, which is a finite mapping. And so that space better have at least dimension 3g minus 3, but in fact it has to have dimension at least 3g because every fiber has dimension at least 3 because you have the automorphism group of P1 acting. So this is what's risky. So he said, okay, I've got a permutation group with at least 3 G generators whose product is 1, satisfies the Riemann-Hurwitz formula, and the point is he reduced to the primitive case. So if this group's solvable, so is this. And then he proved you couldn't do it if the genus is bigger than 6. And if the genus is 6, you can do it, namely S4 provides an example. There's always a degree, for any genus 6 curve, there's a degree 4 map to P1, and so solvable. Okay. And Zariski actually conjectured the converse. He said, suppose I have a primitive cover, and I have at least 3G branch points, then it should be generic. That's not true. And the first counterexample, and as far as I know, there's only 2 counterexamples known, is when the genus is 2 and you take the dihedral group of order 10, then with 6 branch points, all of corresponding to 6 involutions. And then what you can show is that the Jacobian will always have a non-trivial endomorphism with a specific minimal polynomial, and so it can't be generic. Okay, so here's the theorem. So this is so it's a series of 3 papers, and what it says is that if f xg, so it goes to P1, is indecomposable, xg generic, and degree n, that implies that, and let's assume the genus is at least 4, implies that G is AN or SN. And in this case, so SN, n has to be bigger than or equal to G plus 2 over 2. And AN, n has to be bigger than or equal to 2G. So this gives you Zariski's theorem as a consequence. Of course, the proof does depend on the classification as well. And the key point, again, so you have a primitive permutation group with lots of generators whose product is 1. Now the point is, the index, so if you're not in the case basically, so in this first paper with Neubauer, we basically reduced it to the almost simple case. Okay, then the paper with Magard, we had this fixed point, showed that you can't have very many fixed points except if you're in the alternating group or symmetric group acting on M sets. So that's reduced it to that case. In the paper with Sureshin, which is actually a memoir, we handle that case. The case of where it's AN or SN acting on M sets. So what we prove is M has to be 1. So it's really, it is the N. It's the same N here. That's the point. And so the first reduction, let me go back. I said something about the Tate module, so let me point out a useful point of view in terms of the Tate module. So if you have this set up, well, let me do it as fields. And here, everything's algebraically closed, so I might as well. I'm in characteristic 0 as well. Now, so if this is the symmetric or alternating group, I could take this function field and take the fixed points of a Young subgroup. Let me do the symmetric case. So I can take the curve that corresponds to that subgroup. So this is degree n. So this is the fixed field of Sn minus 1. The genus of this is less than or equal to the genus of this. Y is not a good one. This is just the fact that this genus can be read off of this quotient by the Jacobian of this, which is just essentially the fixed points of u in this action on the Tate module of z. Now you just use the fact that in any module, in characteristic 0, this subgroup has at least as many fixed points as this. That is just Frobenius reciprocity together with the fact that the induced character of this contains the induced character of this. And in fact, it goes up in the whole sequence. So what this tells you, at least if you want to get rid of the Young sub of these guys, it's enough to actually handle the case where it's 2. So if you can show it can't work with 2, it won't work with the other ones, because you have the genus will be too big. Will grow even bigger. Well, as I said, it's a memoir, so even the case of n equals 2 is not so easy. But again, I mean, it's really a mess, and it's hard to even say what the key idea was. It was just, and I think these things can be very messy to deal with. This is why I have to change co-authors after each paper. They get tired. I wear them out. So. What happens in positive characteristic? Well, it's wide open as to what happens in positive characteristic. And in fact, but let me give you one result. So in positive characteristic, you can still ask about what happens, what kind of maps can you have from the generic curve. So if f goes from xg to p, and again, to p1 is generic. You have, let's suppose it's degree n. Well, you can, again, reduce to the indecomposable case. That still is true about the Jacobian. And so we have this case. But one can show that n has to be bigger than or equal to g plus 2 over 2. It's still true. Brian Osserman showed me a very easy argument. It just comes out of Brill-Nether theory. And in fact, on the other hand, he also showed me an argument showing that, in fact, there are such maps of that degree. Because it cut from characteristic 0, and you just sort of reduce, you can get them. I should actually say it was well known that Sn already occurred. The proof that An occurs is due to Magard and Volklein, and that's within the last 5 or 10 years, certainly. And it was not easy to prove that An this does occur. Okay, so we at least know that, but we don't really have any idea of what the possible groups are and whatever. I will say there's the fact that you can't assume that there's lots of branch points anymore. So for example, there is a result of mine with Joel Rosenberg that says that there exists, so for any curve, now we don't have to, for any curve, x of genus G, there exists of degree n equals 3pg plus 2 with f ramified only at infinity. Or at points over at infinity. So unramified over A1. So you've got the absolute worst situation. There's lots of wild ramification. And to try to describe these situations, and I have no idea whether this is anywhere near the right answer. It's pretty easy to see n has to be at least that, and it's also easy to see that n has to be at least p, and in fact we can prove n has to be at least 2p, because there has to be wild ramification. So your group can't have order prime to p. Okay, so the existence is actually fairly easy. It's just mostly Riemann-Roch and messing around. The analog of the which I've now erased, the Greinlich-Thompson conjecture and positive characteristic. So there is a conjecture that I made which says that the composition factors would be alternating cyclic or groups, Chevrolet groups in the natural characteristic. And in fact, you can, Abiancar has produced examples which show that in fact all of the classical groups do occur. So, and I also have a result which says that in fact, if you have Chevrolet groups not in the natural characteristic, and you fix the rank, then there are only finitely many field values which actually do occur for a fixed genus in terms of the rank. It's possible that there are large ranks where you can still, the size of the field might get bigger as you increase the rank. But in fact, that was based on what Martin and Jan had done, that was sort of the situation in characteristic 0 originally, that you couldn't control the rank. Okay. So let me, the last 15 minutes, switch to, so this, what I've been talking about so far mostly has been geometric. I've worked over an algebraically closed field. So let me work over, do some arithmetic now. Okay, so here's another definition. So F in the same setup is called exceptional. If you take the fiber product of these things, so in other words, you take the set of all pairs you look at this variety, if this has, and then throw out the diagonal, has no components, no absolutely irreducible components, defined over K. So the Galois group, the absolute Galois group of K, X, has no fixed points on the component. For a polynomial, suppose that F is a polynomial, what is this saying? This is saying that f of x minus f of y over x minus y has no absolutely irreducible factors over K. So over finite fields, these come up very naturally and go back quite a long time. So if K happens to be finite, and then F is exceptional, so and let's say Q is big enough. I won't be too precise. But anyway, F is exceptional if and only if F is bijective on Q rational points. So F takes the Q rational points into the Q rational points of Y, and it's bijection. So if Q is small, of course, it's not saying very much. If Q is field of two elements, saying that f of 0 and f of 1 are not the same for a polynomial is not a huge restriction. So for polynomials, the best known result, I think, at this point is if Q is bigger than n to the fourth, where n is the degree, then you're OK. Exceptional always implies bijective. It's going back the other way. That's not true. OK, and so people have been looking at exceptional polynomials back in Dixon's thesis. He thought about back in the 1890s. He looked at exceptional polynomials. So what can you say about them? And I don't think anybody ever thought they would, certainly nobody ever conjectured that you might be able to classify them. They asked about the degrees, they asked about various things. But in fact, You can say quite a lot. But before I do that, let me point out what it translates into group theoretically. So I'm in the case of, let me just stick to the case of a finite field. You can say what goes on in the general case. But so A mod G is cyclic in this case, or over a finite field. And so what it's telling you is that if A mod G, say, take a generating coset for A mod G, then exceptionality is equivalent to saying that every element in that coset has exactly one fixed point. Again, if you're a permutation group theorist, you say that's a bizarre condition. And again, not anything that probably people would look at. And certainly I don't think had looked at. It turns out the average number of fixed points for an element in this coset is 1. So in fact, having a unique fixed point just means if every element has a fixed point, it has to be unique. So there are various examples, which I don't have time to go into. I mean, not all that many if you think about it. But for example, Frobenius groups, where A mod G is cyclic, G is the Frobenius kernel, for example. Okay. So here's the theorem. Suppose that f is exceptional. Let's say polynomial. Actually, for the first part of the theorem, all I need is a totally ramified point. I don't need it to be a polynomial. With degree n. And assume f is indecomposable. It turns out it's not very hard to prove. You have to do a little bit of work. But certainly, if you have a composition which is exceptional, then it's bijective. And so it's bijective on each piece as well. So every term has to be. But in fact, the converse is true. So a composition of exceptional polynomials is exceptional. So you can reduce to this case. Then one of the following. P is the characteristic. So, and in this case, the group is affine. So there's a normal elementary abelian P subgroup. This case, well, okay, I'll stop. N is prime, not P. And basically what you have is f of x is essentially x to the r, up to linear equivalence, it's a n. Or it's a Chebyshev polynomial, essentially a Chebyshev polynomial. Actually, slightly more general, can be what's called a Dixon polynomial of degree n, where in this case, n has to be relatively prime to q minus 1. And in this case, n has to be relatively prime to q squared minus 1. So the Chebyshev polynomial is the polynomial that relates the cosine of n theta to the cosine of theta. And then there's you can put an extra parameter and sort of twist it. And I think Dixon defined this in his thesis. Or C, P is less than or equal to 3. N is P to the A times P to the A minus 1 over 2. A bigger than 1 odd. And in this case, G is PSL to P to the A. And P is the characteristic lemma. So notice in characteristic 5, or bigger, it says there's just Chebyshev and powers and these things. And there are lots of examples known in this case. And in fact, theoretically, there are known other examples. Peter Mueller and I, and then later Mike Z, produced some examples that weren't known. And we, at least I think that probably we know all of them, except perhaps a finite list of them. But that's going to take a long time to ever do. OK. So again, this was pretty much, we translated it to group theory and solved the group theory problem. And what very recently, but again, now it's pretty easy to show that, in fact, well, these clearly work, so there's no problem. Here, there are examples of that. But here we have the group theoretic solution. So do they actually exist? Well, in fact, they do. And it's not very hard to see that there are examples, because so what you have to do is produce a curve. So the idea here is to actually produce the L upstairs at the top, in which the group acts on it, and then get the whole picture from that. And in this case, these are PSL2Ps. They act on a nice curve, P1. And so you can get examples where the top thing is genus 0 is a P1. So that shows that they all exist. But you'd like to classify all examples. And in fact, there was an industry for a while producing examples. Lenstra and Mike Zeev and Cohen and Matthews produced some examples where the genus wasn't 0 at the top. And quite recently, in 2 papers, I guess, so Rosenberg and Zeev and Gorelick and Zeev, so in 2 papers that should hopefully be appearing 2009 in the Annals, we actually classified all the polynomials in this case. I should say, especially since Jan is sitting here, this was a joint paper with Mike Fried and Jan. And so we actually classified the polynomials. And we actually produced a new family that wasn't known by doing this. Lenstra made the observation, which I completely disagree with. He said, all group theory is good for is telling you where not to look. I'm not sure that's true, because I don't think nobody looked here. So it wasn't just not knowing where to look, not where to look, but also where to look, it tells you. So, and I still don't even agree with that statement. So I think he was doing that to needle Fried, though. So I didn't take it personally. So we classified the polynomials. Well, how did we do that? We did it in the same way. So we observed that, OK, we from the group theory setup already here, we proved exactly what the inertia groups could be and what the ramification would be. So there's always wild ramification in this setup. And but we figured out exactly what the higher ramification groups are. So we could compute, for example, the genus of that Z from that in the various situations. And then the point was we needed to construct that Z, or try to classify all such Z that would admit this group acting on it. And it turned out in almost all cases, the Z there, if you took sort of the CeLO P subgroup in here and took the quotient of Z by that, it turned out in most cases it was genus 0. And in the cases where it wasn't, it was at least hyperelliptic. And so in the case where it's genus 0, the Z is an arbitrary extension of a P1. So you have a nice way of parametrizing those. Even in the hyperelliptic case, you could still do this. And so we then could identify Z, the possible forms of Z, see which ones admitted the group, and then classify the curves. And from that, we can actually then write down polynomials. When anybody asks me to write down the polynomial, I say for me a polynomial is a group with an action and a family of inertia groups. If you ask Z, he writes down the polynomial. So if you want to see the polynomial, either look at the paper or ask Z. They actually have fairly nice forms. OK. So what if it's not exceptional? I'll just end with. Then it turns out there's still a very nice connection with permutation group theory. So for example, here's one theorem. F not exceptional. So F, let's say a polynomial. And let's suppose the degree of F is prime to the characteristic. Then so now what I'm going to do, I'm starting over FQ. I'm going to grow the field. Let's take A to be relatively prime to the index of this A. So that means A doesn't change as you go up in this tower. Well, that's not saying much. So you roughly miss at least a sixth of the points. Well, the reason is where delta is the proportion of elements in the coset AG, the same setup I had here, that are derangements. So again, it comes back to some classical problems in permutation group theory, how many derangements there are. And in fact, I think there was a question that Cameron and Cohen answered in '93, which I think came partially from you and partially from Lenstra. How many derangements are there in a group of transitive group of order n? And the proportion is at least 1 over n. Now we're in a slightly more general situation because A is not G. So what I proved with Daiqing 1 was that if you look in this coset, either there are no derangements or the proportion of derangements is at least 1 over n. And in the case where you have a polynomial, the proportion of derangements is at least 1/6, so it's bounded away from 0.
A at least 2, of course. Yeah.
I think I said n was always,
N, but what's the A, M, A, not N.
yeah, okay.
F2 is bijective, isn't it?
No, it's not exceptional, so,
Ah, no, okay, no, then,
no. Yeah, it's actually fine, it's not exceptional.
It's okay with it.
Right. Okay, so let me stop here.